Okay, gonna get started today. We have a big conversation ahead. So just a reminder, we've been talking about the Radical AI Founders Compute Cluster. The applications are still open. I know that there was a difficulty with the link. It is reopened. You should be able to apply. So if you've been having any difficulties with that, it is still open. It'll be open until October 31st at 11:59 p.m. Pacific time. So please, if you have any questions, please reach out. Again, this is your opportunity to get $250,000 worth of credits through GCP. You'll get a year-long of programming with Radical Ventures, as well as the GCP team. It's an awesome opportunity to start building out a product or testing a product if you already have one. So definitely get in on that. If you're unsure about it, I still advise you to apply, go through the application process. If you have any questions, just let me know. But really looking forward to seeing all of those applications. Just a reminder of the timeline, 31st. We'll be announcing the first set of folks by the November 15th deadline. There will be some rolling announcements, so that won't be all, but we will start to announce by November 15th, and then we'll start to do some monthly programming. So you can look forward to that. Again, competitive process, but really looking forward to seeing folks. And as we're doing rolling, if you're unsure, still advise you to apply. This is going to be a great opportunity for folks that need access to computer and are looking to start building. A reminder, this is our community, so we have some guidelines here. If you haven't reviewed them already, please do so. If you breach the guidelines, we do hold the right to remove folks from the community. Please flag anybody if you're having any issues. But generally, I think this is a warm and welcoming place, and we have a lot of ask channels and opportunity channels in the Slack, so please jump in there. Feel free to share information and get talking to people who are in a similar position to you all around the world. Okay, and just a reminder, so this is our last keynote session. It's been such a great 3 weeks. Really looking forward to this conversation. Tomorrow we have our last practical lab. So we are fortunate to be joined by Parisville Patel. He is a partner at Radical Ventures. He leads our go-to-market strategy for all of our portfolio companies. So he has a lot of experience in the consulting world prior to doing venture for years. And now we also have Sean Gardner joining us. So he's from Weights and Biases. He works in the business development sector there, also has a lot of experience. So we'll be able to do some office hours and Q&A with him. And we're really looking forward to that. So don't miss that tomorrow. It's in the calendar. If you are having difficulty with it, let me know. But the Slack information is there for the join link, the timing, the calendar event, all there in that Luma link at the bottom, as well as some more information on what to expect tomorrow in our session. And that'll be our last practical session. So almost there, but really looking forward to this conversation today. So with that, I'm very excited to be joined today by David Barber. David Barber has just joined Radical Ventures as a scientific advisor, so we're very thankful to have him. And he is also the director of University College London's Centre for Artificial Intelligence, and they aim to develop the next generation of AI techniques. Really interesting space. David is also a fellow of the Alan Turing Institute and the co-founder of startups Reinfer and Human Loop, and a distinguished scientist at UiPath. So he has lots of experience, both across industry and academia. So we're very fortunate to be able to learn from him today. And he's here with us. So David, welcome.
Thanks, Leah. It's great to be here. Thanks for the kind introduction as well. It's very flattering. Okay, folks. So yeah, as Leah said, I'm David Barber. So yeah, I'm the scientific advisor. I'm also an academic at UCL. You might wonder a little bit, how my research sort of links to, AI. So predominantly, I'm interested in the sort of probabilistic modeling approach to AI. So, kind of using large scale probability models to think about how we might sort of reason and model things as well. So having said that, I'm also very interested in the applications of AI to, all kinds of problems in the real world, and in particular making startups, because I think that's a very cool thing to do. I've enjoyed doing that very much. I think it's a great part of being an academic, having the opportunity to work with great people, but also to apply them and real world problems is very fun and exciting. And when academic things are very theoretical sometimes and not necessarily having great impact, it's great to see that you can actually have alternative impacts in the real world as well through things like entrepreneurship. So Yeah, as Leah said, I built a few startup companies in AI, so that's been very interesting for me. But I also want to focus a little bit today on not just building startup companies, but also talking a little bit more about the scaling of them as well. So, once you started, how do you grow them, and what are the things you need to think about when we're going to do that? So, I'm delighted to say that we've got Max here, who's basically a great researcher, but he's also now the chief AI officer at Isomorphic Labs, which is a sort of a DeepMind spin out, I guess one could say. And Max is going to tell us, a lot about his experience, and we'll have about an hour's worth of a chat, and then there's something else at the end of that. So, without further ado, welcome, Max. It's great to have you here. Um,
It's awesome to be here. Thanks so much for hosting this. It was great.
you're very welcome. So, Max, I think, probably a lot of people are sort of familiar with DeepMind. It's a well-known thing. They may be, less familiar a little bit with, the isomorphic labs and how that will happen. So maybe we can sort of start a little bit with, go back before isomorphic labs began and start to think a little bit about, what was this AlphaFold all about, and what was going on at DeepMind, and what were you doing as part of that whole AlphaFold team?
Yeah, so actually, going back in time, in DeepMind, I actually wasn't involved in the original AlphaFold. So, I joined DeepMind about 10 years ago now, off the back of an acquisition of my previous company, and I was working at DeepMind on like a whole bunch of different research. I guess lots of like pure neural network architecture research, generative models, learning algorithms, and then I really caught this bug for reinforcement learning, right? It was really the place in the world to be doing that. I think 2015, 2016, 2017, and I caught this reinforcement learning bug and worked on some like really exciting domains there, things like Atari, but then pushing into 3D with things like Quake, Capture the Flag, and worked on the AlphaStar project. That was like one of the key things we were driving. And over all of this time, we were getting bigger and bigger in terms of and more complex in terms of the domains that we were trying to apply reinforcement learning to. But it ended up, these solutions like AlphaStar, for example, ended up not just being sort of a very clean reinforcement learning algorithm. When you actually dug into these methods, they were like much more what I would call just like learning systems, where you'd have a component of supervised learning mixed with unsupervised learning, mixed with reinforcement learning. And then some of this was fine-tuned and, or now called post-trained and mixed together in multi-agent scenarios. So we ended up constructing these really, really like fairly complex learning systems. And a lot of my research began to become, really how do we tackle these very, very hard, ambitious problems and domains that we want to crack by bringing in like the whole world, anything and everything from machine learning and deep learning. And then bring together teams of researchers and engineers to actually make this happen. Defining the problem, the mechanism, the leaderboard, which like can allow a whole group of engineers and researchers to just grind against. So I was doing a lot of this sort of work in DeepMind on these big challenge domains. And in parallel, we had this amazing development of AlphaFold, which actually, like crazily enough, started as a hackathon project. Can we get any signal like by throwing a CNN at that point in time on these protein structures from the protein data bank? And yeah, there was signal there. And then that spawned like AlphaFold 1, which was like a huge inflection in performance with respect to the current methods of the day then. And then there was another huge jump with AlphaFold 2, which really pushed the ability for this model to be solving these protein structures at basically the same level as experimental accuracy. And that really was the what we saw as like the solution point for this protein folding problem, at least for single proteins. And we saw just like I think 3 weeks ago, Demis and John Jumper getting the Nobel Prize for this, which is very well deserved and super exciting to see. So I sort of saw all of this happening in parallel to you know, the much more, I guess, like research that like I was doing, we were doing in demonstrating the impact of AI and what AI could do in more and more complex systems. And in the back of my mind, it sort of always felt a bit unsatisfying that we have these amazing teams and we're like putting tons of effort and working 120% on these really, really hard problems like StarCraft. But then at the end of the day, these neural networks that, you know, they beat the top human professionals, and we have, you know, we learn an amazing amount of stuff, but the neural networks themselves, they're thrown away and they don't actually do anything. And more like the research paper is the artifact. And I love this technology. I love deep learning. Like my whole career has been developing these networks and these learning systems. And, you know, I was starting to think, well, like, where should we be actually applying all of this effort and all of this technology to actually make a real impact on humanity? And, you know, I could see AlphaFold happening and progressing. And then at the same time, Demis launches Isomorphic Labs and invites me to head up AI there. And to me, this was like a no-brainer sort of next step in, you know, to me, it's like, really, how do we see that positive impact of deep learning on humanity? And you know, Isomorphic Labs is essentially taking that initial proof point of AlphaFold that we can get these models that generalize to, you know, vast spaces in biology. And people didn't think that was possible. And people still think that that might not be repeatable. So how do we take that initial proof point and really turn this into something that can have widespread impact on human health? And for us, drug design and drug discovery is really that initial starting point for us.
So Max, going back to, you know, so your story a little bit, I mean, it's very interesting, but it's also kind of remarkable that, I mean, I'm presuming, you know, you don't have much of a strong background in, say, biology, or, you know, the sort of the things that people would traditionally assume somebody who's working in, you know, protein folding or protein structure prediction, you know, that they would have that sort of, you know, be inculcated with this sort of, you know, all that, they know all that stuff. I guess you probably didn't have that. And is it in some sense kind of like a feature that you actually, you know, bringing people in who don't come with that sort of, some people might say baggage, you know, that might have sort of bias them towards certain ways of thinking, that actually, because you didn't have that, or DeepMind didn't have that, that maybe that's why the breakthroughs happened?
Yeah, I mean, absolutely. I didn't have much background in this space. Like, I grew up in like a medical household, but, you know, only sort of basic biology and really undergrad level chemistry with like from like a more general engineering course. And so coming into the drug design space, there was a huge amount to learn. Like, and it really, to me, actually, it was an amazing feeling. It felt like being a first year PhD student again, where everything's going over your head. Like, there are tons of words being thrown at you, tons of concepts, and you don't have a clear mental model of how all this fits together. And so, you know, like, I mean, I'm constantly still learning as we get deeper and deeper into biology, but especially over like the first year or two, like really getting to grips with the chemistry and biochemistry side of drug design was a really exciting thing. I have an amazing, very patient colleague, Caroline Lowe, who was also part of this like founding team, and we used to just talk for hours on like, how does drug design work? How does this chemistry work? Like, how do you actually like modulate a protein? What does that mean mechanically? And actually, the really cool thing about this space, especially the biochemistry space, is that this is actually a very mechanical thing. When you start looking at the 3D structure of proteins and wanting to modulate the function of these, this means actually creating other molecules that will come in and stick to these proteins and physically change the shape or physically disrupt the surface as it would be interpreted by another molecule coming in. So this is actually like a very mechanical thing, which suits my sort of visual brain, and was fascinating to learn. I think it is a feature rather than a bug of not knowing and being a bit naive. when I think about like the hiring in our machine learning research team we've done over the years, I would say probably like 60 or probably 70% of the machine learning research scientists have no domain knowledge. So they've never touched chemistry or biology before. And, you know, again, just like me, have like learnt on the job about biochemistry, about drug design, about biology. And, you know, I think credit to like the interdisciplinary culture we have at ISO, that you can actually sit next to a chemist or next to a biologist and they will give you the time of day to talk through the naive questions. But what I think what this really helps is, as someone who's naive to the field, and I think it applies to anyone going to like any new field, if you come in with like a mindset of curiosity and you want to learn and you're not afraid to ask the stupid questions, you can start to approach things from like a first principles thinking perspective. And so instead of because you don't know the terms and the glossary, you know, of which, and I always think language and these complex terms, they hide a lot of the detail behind them. So you can, instead of talking in that language, you have to talk in simpler terms because you simply don't know that language. And so you end up approaching these problems from naivety, from first principles, and questioning every single assumption that people have made over the last, you know, 3 decades of drug design. And many of those assumptions are there for really good reason. And some of them are historical artifacts. And when you start thinking about, okay, but now we've got this model which does X, does that really mean we need to do Y? You know, can we just completely remove Y and remove it as a concept? And all of these sort of things start to fall out from that. So I think actually approaching new spaces from a point of naivety can be really, really powerful, especially, you know, you need to have that team where you do have the real domain expertise with you. But suddenly we've seen that this has been a huge asset. So having chemists who are really open to educating machine learners like myself, and having machine learners that are really open to educating chemists, means that you can really bring like world-class expertise from both disciplines and together, where, you know, a single person might not have world-class like expertise on both of these domains.
And how does that go? You know, so I think just kind of like a common sense folklore almost, that, you know, it's kind of easier for a machine learner, say, to learn something about biology in this case than it is, say, for a biologist to learn something about machine learning. Is that a fair statement, or is that not your experience? Are they also very willing and able and to get stuck into some of the machine learning details?
I think people, I've seen people being really willing and wanting to get stuck in. You know, we even run a like introductory machine learning course for like new starters who want it. You know, building up from plotting a line on a graph to like linear regression to you know, what a neural network is. And I think the key thing is, it might be hard to like really understand, like, you know, at the very core, the nuts and bolts, if you haven't been in the trenches writing and dealing with the nuts and bolts. In the same way that I will probably struggle to really understand at the core some of the things in biology unless you've really been on the lab bench making those mistakes firsthand. But I think still in both cases, you can build huge amounts of intuition, and you can create these mechanistic mental models that really can serve like the purpose of understanding like a particular field, how this all fits together. And you know, I've seen chemists make like incredible, like have incredible intuitions on new models that we're developing, and you know, new ways we could advance the like even some of our training algorithms. So I totally see it's possible.
Well, so let's talk a little bit about the sort of the commercials. So I mean, it kind of, I guess, you know, so Isomorphic was spun out of DeepMind. It kind of focuses on drug design, discovery, etc. But, you know, how are you going to get, what's the commercials here? You know, how are you going to make money out of this? I mean, what's the sort of, you know, rationale and the sort of the mechanism behind that?
Yeah, it's really interesting. You know, drug design is one of these spaces where actually over time, it's become harder and harder to design a new drug. You can look at a graph of like the cost essentially of a new drug, or like the number of new drugs being created per $1 billion of R&D spend over time. And this is actually exponentially decreasing. So it's becoming exponentially more expensive to create a drug over time, even though there's been like so much technological progress over this time, which is kind of mad. But I think it really reflects the fact that there hasn't been great technology to help us find new drugs. It's been very empirical. The field, like the type of research, is literally called shotgun research, because you're, just trying to find these molecules by random chance through screening empirically in the lab, lots of stuff. But when you do find some of these molecules, they're incredibly valuable, both from patient need point of view, literally being the first treatments for new types of cancer and these sort of things, and also from a financial point of view, where a new drug blockbuster drug can be making billions of dollars a year in revenue. So really, the commercial side of Isomorphic Labs is about, well, how do we take this amazing technology that we have and what we can build to really drive a pipeline of molecular assets. So these are drug molecules that you develop, you design, and then you develop into the clinic. And as you show efficacy, they build and build in value. And you either license these out to pharma partners to, develop a market, or do that yourself. So really, we're in the business of creating new drug molecules to really impact patients at the end of the day. And for us, all of the machine learning models and research there is to radically increase the success rate of this design, the ability to go after diseases and drug targets, so proteins that no one has ever been able to go after because we just don't know how, and to do this a lot quicker and to do this a lot cheaper.
I heard some figure, like the number of sort of active molecules that people are using in drug treatments is not that many, right? It's something like the order of 1,000 or something. Is that correct? There's actually really very, very limited number of sort of safe molecules that you can actually use to treat people.
Yeah, I'm not sure the exact number, but it's not a large number. We're not talking tens of thousands of molecules that have been to find these drugs that actually work very well, that are very safe, is hard to, even further, if you want these drugs to be taken as a pill rather than be injected, that's even harder again. And that's what we're focused on. We're focused on what's called small molecule drug design at the moment, where small molecules are these molecules which you could take as a pill. To do that, it's not just about how do you modulate these proteins, but you also need these molecules to be the right level of solubility, to be able to permeate through the gut, to get to the right part of the body, to not be broken down by the liver as they're flowing through the blood. So there's just so many different challenges along the way. AlphaFold was this amazing like proof of concept that we could start to create this type of model, these sort of foundational models for biology. But really, we see there's like half a dozen more AlphaFolds that we've got to create to really crack this problem and see this step change in output.
Yeah, and I guess there's also eventually, I guess it's like a feedback mechanism, right? Where you might say, okay, here's a set of sort of potential drugs which might be useful, but then somebody's got to go and actually create them, build them, test them, and then there's this sort of feedback mechanism where you say, okay, that one didn't work so well, this one seems to be not too bad, and then you need to sort of iterate in some efficient way, right, to sort of keep that going.
Yeah, absolutely. I mean, the wet lab side of drug design, so that the actual experimental steps, like these are the bottlenecks, right? It just takes so long. To even just like synthesize the molecule that you want to test, that can take 1 month, 2 months, 3 months. It depends how hard the chemistry is for this. Potentially you can buy molecules off the shelf, but then you're limiting, your search space to just molecules you can buy off the shelf. And then, that's before you even test these molecules out in a real, assay, a real experiment. So, if you think you have some great molecule designs, it can take 3 months to actually create them in reality, test them, and get the results fed back. And we need to be doing much, much better than that, and bringing more and more of this experimentation in silico, i.e. on a computer, to be able to make much more efficient use of the wet lab time that we do take is one of the central forcing functions for us.
Yes, I actually wanted to ask you a little bit more about this, AI for science, right? I mean, it's a big deal right now. Obviously, in some sense, you guys are in that game as well. But I guess, you could think about this kind of two strands to this, right? I guess one of them might be, you might say, well, look, we have these classical, say, models of physics, or in this case, chemistry or quantum chemistry in this case, and you could try to simulate or to actually, evolve those equations to some extent to sort of simulate what's going on. I know that the number of nanoseconds, even we thought you can actually do this reliably, is very short for classical ways of doing it. But then there are these sort of AI techniques that can accelerate the simulation of physical systems. People have done that quite extensively in fluid dynamics and other areas as well. So there's a kind of is sort of a way to sort of go back to the original physics, but sort of accelerate that physics, but sort of try to stay close to the physics. And on the other hand, there's sort of these much more sort of agnostic to the physics sort of systems where you might sort of say, I don't know, have some very generic model like a transformer or whatever it may be, or deep learning system, and you try to impose some of the kind of constraints that you feel need to be there, in a sort of a physically meaningful system, some symmetries or whatever they might be. And these are kind of different approaches. So obviously AlphaFold is on that sort of second strand of thinking, but what is your feeling generally about the first strand? I mean, is it a sort of likely to ever be successful, in, for example, areas like, say, chemistry simulations?
Yeah, it's interesting. I think these two areas can work together very, very well. It's crazy that if we're working in the domain of physics, we can often write down a lot of the theory by hand with maths, and create even coarse approximations of things like the unfolding of the universe millions of light years away. But we can't do that with, for example, the dynamics within our cells. And, as you alluded to, we can write down the physics of how atoms interact. But then if we wanted to scale up, that unrolling of that physics to the trillions of atoms within our cells, that's just completely unfeasible. And it's we just haven't worked out how we can model things like the cell at a coarser scale that we could, and a simpler way that we could write down by hand. And so that leads us to that sort of bucket two of, instead, let's use, machine learning. How does this work? Well, we record snippets of data of this system, and then, ask our neural network gods to just learn the abstractions and theories and equations internally in the activations of these neural networks. But of course, there's a big trade-off between these two regimes of, a physics simulator, and then you can, obviously train an AI, like a machine learning potential, a machine learning force field or acceleration on top of that, and these more black box models like AlphaFold. And the big difference is in the generalization of these models, right? So with the sort of bucket one, these physics simulators and even AI accelerated physics simulators, they generalize a lot better because these rules are fixed, and so you can just keep rolling them out. But they're very, very, very sensitive to initial conditions. So if you get the minute thing wrong at the initial condition, all these complex interactions add up the wrong way, and you end up unrolling into not the space that you should have done, and it's really hard to tell this non-reality from the true reality you were trying to simulate. On the other hand, you've got the like black box transformer, which you can put any input in and you'll get an answer out, but how can you trust that that's the right answer? And as you start to move away from your training domain, your model will generalize poorer and poorer. I think there's a really cool space which is like this in-between space where, as you alluded to, you can start baking in some of these like physics assumptions into our networks. So, constraining some of the operation of these networks to obey physical laws. But there's another way, which is think about, okay, well, in the part of space that we can simulate, maybe at the scale that we can simulate, let's create data and use that to train these more black boxy models. And maybe the black box models allow us to scale up in terms of the initial conditions that we can create to then create more data to train bigger black boxes. And maybe there's a bit of a virtuous loop that we can create. So I think there's like a lot of exciting, a lot of exciting work that's being done along these veins of actually marrying the sort of black box, flat transformer world with the much more structured physics simulator world.
Yeah, actually, many years ago, when I was a young naive researcher, I'm now an old naive researcher, but I came across this protein folding problem. I was probably in my 20s, and I thought, wouldn't it be cool? I had some small database of three-dimensional geometry of the atomic structure, and I thought, wouldn't it be cool to actually write down some kind of some meta level model, right? Something which is something like say force field based things, so that there are interactions between these sort of molecules in three-dimensional space, but they weren't sort of predefined by some Coulombic interaction. They were going to be learned. I would actually learn the parameters of these models in order such that it would actually replicate as accurately possible as the known structures that we had. And it was interesting actually. It worked, back in those days. This is 20 plus years ago. It was actually quite interesting that it sort of worked at all. But it's interesting, I think, I think it's a little bit along those kind of lines that in some sense, it had some elements of the physics there, but actually, the physics doesn't necessarily fully replicate the real system anyway. So you might as well say, well, okay, there are some free degrees of freedom that you can actually learn these models such that they will actually better replicate the real physics. It's also interesting actually with DeepMind, right? The weather stuff is also reminds me a little bit of this, kind of situation as well, right? I guess I haven't, read those papers in any great detail, but that sort of, that traditional sort of, you just simulate this thing as some enormous Kalman filter. And I think the UK government, historically the Met Office is one of the biggest users of supercomputers globally, actually, to try to predict the vagaries of the British weather. But now that's all doable by this sort of semi-physical machine learning models, which DeepMind has also been a very sort of strong proponent of that.
Yeah, and it's really cool to see these weather models emerging. You've got models for materials emerging. You've got, as you said, like fluid dynamics and like finite element style models emerging. I think the big game in this, like AI for science, is like how do we take these, like the theory and priors that we know about, to be fact, and how do we embed that theory into these networks? So how do we like embed these priors into these networks? And then it's like there's a dial of how strong do we want these priors to be adhered to? On one end of the scale, we've got like, your amazing molecular simulations where you're learning the force fields on like which is very constrained, and on the other end you've got a flat transformer, which can do anything they want with these priors. So
Max, maybe just before we talk more about startups and companies and stuff like that, maybe just ask you one maybe slightly philosophical question. So some people might say, in a way, science is changing, right? Because the traditional approach to science is very reductionist. You say, well, I'll have this physical system. I'll try to break it down into some, well understood, micro level interactions, physical laws, etc. And that it might be difficult to simulate it, but at least I kind of understand it at the deepest possible level, right? And then on the other hand, you now got these sort of kind of machine learning approaches where they say, well, to some extent you might build some physical things in, but it's not necessarily fully reductionist. And this is it clashes for some people. They find this kind of like a kind of an unfortunate philosophical situation that, are we giving up on reductionism in doing this?
Yeah, it's fascinating to see this unfolding. I'm probably like the wrong person to ask here, because I don't really care too much about the understanding. I want to use this, use this science to be able to like build something, or to like engineer a system, or to affect some change. So like I'm very much of the like empirical mindset of, look, if we have this function and this function seems to be predicting very well, and maybe we can understand something about the like error bounds of this function in different parts of like the space of applicability, well then that's great. Like, and if that allows us to understand and affect more in our universe, then I'm happy. I'm personally happy with that, and don't need to have this like reductionist understanding. But I've got a lot of very close colleagues who also want to have that reductionist understanding and really understand this, because at the end of the day, that does help you work out where you can apply this this function. So yes, it's a little bit sad in the sense that it's becoming more and more black box science, but I think it's also just amazing how much these black boxes are opening up in terms of what we can affect in the world.
Cool, great. So let's talk a little bit more about the companies and startups and entrepreneurship and whatnot. So let's think a little bit about, say, talent, right? So maybe I guess in some sense you might think there are three areas, right? With you might say traditionally that you need to sort of nail if you're going to make a company in AI. So one would be talent. Clearly you need good people. You're probably going to need data, in some way. Maybe that's increasingly important. And compute, these are obviously three, major ingredients. But so maybe you can talk a little bit about that. But also, are there more? Are there more than those three, or and how do you get all this? How do you get talent, and how do you get data and compute, and maybe some of the other missing ingredients that I didn't mention?
Yeah. I think like talent with data, and then the compute and engineering infrastructure to support that, I think are like the key ingredients for actually like developing this sort of technology in a commercial sense. And if we're thinking about talent, like especially now, AI talent is just so in demand. It's I think probably anyone who's got a company in this space will resonate with the struggles to find the best people, attract the best people here, retain the best people. At the beginning for us at ISO, like this was hard, and this is even us coming off the tailwinds of DeepMind and AlphaFold with a lot of prestige behind that. Like we're very, very proactive with our AI talent hiring. Like we ask everyone in our team to like really be using their networks and personally reach out. Like I think it's it resonates so much more with people when you're connecting with a fellow scientist or a fellow engineer versus like a recruitment team. So we do a huge amount of like proactive outreach. Also, for a niche domain like ours, you're not going to have, kind of like we talked about before, there's not going to be a huge pool of people in the world who've been doing AI for drug discovery. And if they have been doing AI for drug discovery, it's probably for the type of models that we don't use because we built new models. So like a lot of focus for us was as we talked about, not focusing too heavily on people with the domain experience, but thinking about who are going to be those generalists, those generalist machine learners, those generalist engineers who can actually learn this domain and make the transition, and actually are just perhaps like really high agency people who will again thrive in like the small company culture. So I think that that's been a key thing for us. Really looking at where the talent is coming from. Like, so who are the key labs out there, the key institutions or companies that are like emblematic of the type of people that you want to be hiring, and literally going out and connecting with these labs and people and building those relationships over time. And these, like, all of our fields are like, they're pretty small, so you're going to be seeing the same people over the next 5 or 10 years. So there really is a lot of opportunity to build relationships there. And I think what is also true is you have to start leaking a bit of what you're doing, right? So it's really, really hard if you're in pure stealth mode to be attracting the best people, because they kind of want to know what they're going to work on. Why is this a great company to work with? What's going to give you guys the right to win in this space? And so, like, working out ways that you can leak your ambition, your methodology, like how cool the stuff you're working on is also really critical as you start to engage with these people.
What about you mentioned like high agency is a kind of characteristic that you're looking for. I mean, what other kinds of, so in some sense, like, maybe the large corporate culture, is very different from the smaller startup-y kind of scene. But what kind of people are going to thrive in, say, a lab like yours, or what are you looking for in terms of their personality?
Yeah, I mean, I've seen people come from both, like, straight from PhD labs, from small companies, from big, large corporates, like, all be very, very successful. I think there are a few, like the key, like some of the key characteristics we look for are, this notion of like high agency, like people who.
What does that mean? Yeah, exactly.
Yeah, you kind of like, and I think it's like mixed with this notion of curiosity, like, and a genuine curiosity of people who are like seeking out the information, seeking out the answers, like that proactiveness to engage, proactiveness to build, to ask the questions. If you're walking through a very ambiguous build out, like research phase or build out phase of a company, I'm not going to be able to tell my team, hey, this is exactly what we need to build. There's huge amounts of ambiguity in exactly how we're going to do things, or even exactly what the goal is. Like, that might change over time. But having the people who can be comfortable with that, or just enough people who are comfortable with that, who can start probing that, can start put their own meat on that bone, is like super critical, especially in these like early phases of a company where there is just a lot of ambiguity and there's a lot to be defined. So you wouldn't, I'm not going to be able to write out a design doc specifying, the exact scope of a project or a build out. It's going to look quite differently, and for some people that's really, really exciting. For other people, that's terrifying.
Yeah, and if you were to, I don't know, let's say you were to start a company yourself, next week or whatever. I mean, what are the sort of things that you would advise people to bear in mind? So is it, again, thinking about those things, like there's obviously talent, it's important. The personality of the people on the team is maybe very important. But there's these other things. I know, is data the critical thing now, or is it the models? Some people might say things are getting very commoditized in terms of models, particularly if you're talking about things like, these LLMs or foundation models, maybe that's all kind of going to be commoditized in a few years' time. So if that's not going to be the thing, then is it privileged access to data? Or, where is, taking a hypothetical, where would you, what would you be looking out for? How would you advise people to, what do they need to look out for in terms of those kinds of aspects in building a startup company?
Yeah, I think you can be sitting on a state-of-the-art model and new performance that no one's ever seen before, and that's amazing. But these models are quickly commoditized. It doesn't. I think, crazily enough, we've seen it doesn't matter whether this is a large language model that's taken $1 billion to train, or if it's like a model that's taken a couple of $1,000s to train. These are pieces of software and are very reproducible by themselves. So actually, your edge on the model side probably doesn't last very long. You can obviously try and create the research machine that always keeps you at that bleeding edge of modeling capability. And actually, this is a big part of what we do at ISO, but it's hard and it's expensive as well. And crucially, there are other key moats and competitive moats that I think you should look for as well, which and those would be on the data side and on the market side. So on the data side, data is the lifeblood of these models. And if and more data is becoming an actual key competitive asset that can be unique to your company and can really differentiate the company and differentiate the capability. So even though the model can be reproduced, the actual capability can't be, because it relies on the data. And working out how to get into that regime where you have that competitive moat due to a data asset can be really powerful. And then, of course, again, when I say market, this model does something. It has a capability, but it that by itself probably doesn't just produce value. And if it did, then, as this is quite easily reproducible, it's probably not protected value. So working out how you can really deeply integrate that model in a vertical sense to actually drive some sort of differentiated value to this market that you're trying to target, that can be much, much harder to reproduce than even a state-of-the-art machine learning model. And I think really making sure that you're focusing on this deep vertical integration that actually goes out to target the market that you're trying to capture is of course the core thing you should be doing in a business.
And are there any sort of areas that are in your view are maybe underexplored at the moment in not necessarily totally virgin territory, but are there kind of clearly areas where you think there's a lot of scope for doing the kind of thing that you just talked about?
Well, I think data is still fairly, as you move into a new field, data is probably going to be that key space where, especially as a commercial company, no one's probably put enough effort into it. So you might move into a new domain or a new market, maybe off the back of some academic research. Academic research often uses a benchmark data set or something that's been collected with a low dollar value against it. So there's a huge amount of opportunity as you go into a commercial market to really pour investment into that data side of things. And that could even just mean bringing the world's data together and harmonizing it and making it accessible for machine learning in a way that's just never been done before. I often think about, these legendary hedge funds, things like Renaissance Technologies, where you had these whole data teams, people who were just obsessed with going out into the world and just finding any and all possible sources of data, ingesting them, harmonizing them, making them accessible to statisticians in the hedge fund case, to get trading signal from. And we should be doing the same thing for our machine learning models, having people obsessed with finding that world's data, generating like ourselves that data, commissioning that to really to then really be like feeding into our models to be training the best possible capabilities we can be. And I think this is like, you know, an often overlooked space, especially when people are starting out, that can be invested in and create like a key competitive advantage that's very hard to reproduce.
Great. So maybe just a final couple of questions. So what are you most excited about? I mean, you know, this, you know, it's obviously very cool, this, you know, Isomorphic Lab stuff, and there's a, you know, a great you know, and admirable sort of, you know, ambition to do this. But are there sort of, you know, what is this going to really lead to? I mean, is it are you just driven by the kind of the passion to say, you know, find a new treatment for cancer, or is there an intellectual sort of passion there that's sort of like, well, this is never been done before, so this is driving you, you know, getting you out of bed, like this is a really, you know, fantastic intellectual challenge. I mean, what excites you the most? You know, it might of course be a combination of these things as well.
Yeah, I mean, like you don't start at like this isomorphic is a new bet in alphabet, and you know, really to be a new bet, like you've got to have like very big ambitions. And you know, I think for me, it's really drug design is this amazing application of how we can start to like modulate our biological world. But there is actually this bigger, you know, this bigger dream of really realizing the potential of digital biology. So the ability to like deeply understand our biological world. And I think this can have like many downstream applications over the long term. Drug design is like, you know, maybe this first big one that, you know, we're going after and super critical. But as we start to understand things better, and crucially, like understand to the degree that we can actually start to manipulate and modulate our biological systems, like this could open up like a huge amount, which is beyond just drug design, which could like impact human health and you know, even other spaces like agriculture and you know, just yeah, there's a lot of potential here. So I think really hitting that like big ticket item of how do we understand our biological world with this amazing technology that we've, you know, been developing of machine learning and deep learning. That is like the central thing that drives me. There's potential to create these artifacts, these neural networks that are effectively, you know, AI analogs of this biological world. Like it's the equivalent of the, you know, theories and maths equations for our physics world. To be able to create these, to then ultimately like affect change in our real world, that is like the, you know, the real thing that gets me out of bed. And I think, you know, drug design is this incredibly exciting, you know, very high impact, very tangible way to see that happen day to day. Yeah.
Wonderful. Great stuff. So I think that's a good point to see if our folks have got any questions for us. Thanks.
Yeah, absolutely.
Max.
I can come
Yeah,
in
you can
and
probably
help you
cheers.
out. Yeah, no problem. So looking at the chat, we have a few questions that have been upvoted. So thank you both. This has been such a great conversation, and folks have engaged with many questions. So looking at the most upvoted ones, taking a step back into research, I know we're talking about commercialization here. Osman's asked, what AI or machine learning research topics excite you the most nowadays? And if you were to start your PhD or do an AI startup today, what are the most interesting problems that need to be solved?
David, I'll let you start this one.
Well, I think there's so many actually. I'd feel like the way we do work is changing a lot. So I feel like you know, a lot of people do kind of fairly mundane things sometimes at work, you know, like I don't know, maybe a very prosaic example is things like taking information from, you know, something written down like an invoice and then putting it in a computer. And I think that clearly is going to be automatable. But I think, you know, there's this new sort of passion and craze now about agents, right? That somehow go much further than that. But they sort of, you can now tell a computer in natural language, please go and book me a flight from A to B, and it will carry this out. And that's in some sense a very interesting problem from a sort of academic standpoint, because it really goes to the heart of what AI research has been about, since its inception, which is, understanding language, reasoning about what to do, but actually then taking actions in a real or a virtual world and closing that loop, and then sort of seeing what the effect of your actions is. Maybe you might need to type things in a computer to actually then respond to how say the machine is, the website might be sort of presenting information to you in terms of your flight booking. So this is I think it's a kind of very interesting area. And if you can do that well, what does it mean for our sort of world of work? Can it help us to work alongside these sort of systems in a much more interactive and a deeper way for them to really enable us to do cool stuff? And I think that's a very interesting thing. I think there are some very interesting things that will happen, I suspect, quite soon as well, where, currently we're very used to interacting with these systems in a sort of textual way, but it won't be very long in the future when we'll be, talking to machines, and the machine will actually look like we do. There'll be a kind of an avatar, but it's probably indistinguishable from a real human being. And what does that mean? And will it understand our whole history of what we like, what we did last week, who our friends are? And if we can do this well, I think there are really cool possibilities here. I think it's a very interesting space. I think it will be a kind of transformational stage for the way we think about how we interact with machines, but also potentially how we go about doing our daily jobs. And I think we're going to have to try to figure out how to leverage this amazing technologies. The fact that these systems know potentially much more than any human or group of humans could ever possibly know. How are we actually going to take advantage of that? And that's a hugely exciting research topic, and it's also an increasingly hot area for commercialization as well.
Yeah, it's really interesting. I think on my side, I'm just constantly amazed at how good we're getting in terms of creating generative models. When you look between like our amazing diffusion models and autoaggressive models, we're basically able to eat up any data modality now and create amazing unconditional generative models, but maybe more interestingly, like these super conditional generative models where now you're effectively modeling this like natural process, this natural distribution of data that comes from the real world, and with this like amazing amount of conditioning of different inputs, you can start to modulate this as if it's the real world. And that's really exciting, because you can reduce experimentation in the real world and bring it into a computer. And then of course you can start thinking, well, maybe I can use this a bit like a world model. This could be my game environment. And now we can start creating agents that start probing this conditioning and querying these generative models to actually, push these models to create new insights and push it into completely novel spaces. So being able to like automatically in silico with agents, like query these generative models, create new discoveries, is super exciting to me. And working on, both sides of this, the generative models, the agents, and then how this all comes together, I think is, we're really in the infancy of this. We're starting to see like this actually not being science fiction, this actually emerging. And yeah, this is very exciting for me.
Awesome. Thanks both. I think I agree absolutely. The opportunity of agents is very exciting, and our ability to start to modulate and reduce experimentation, obviously exciting, and new discoveries are always encouraging. Jesse in the chat has a question that looks at the opposite side. I think we've talked a lot about opportunities and blue sky vision. Jesse asks, what limitations do you think the current state of AI technology has, particularly with respect to drug development and between molecule development and formulation? Which do you think the current state of AI technology is best suited to address, and why? And more broad on this question, I think, just thinking about the limitations and challenges of technology as you build out your business, could you give us some of your thoughts around how you deal with this?
I'll let Max go first with the biology molecule stuff.
Yeah, sure. I mean, I think limitations of like the models we have at the moment and this technology, it's still very data hungry, right? And we still don't really have a good handle on how we can control the degree of generalization to different parts in data space. And so we try and mitigate that with like creating more data and like all the things I was talking about before. But fundamentally working out how to make much more efficient use of the data we can collect, especially in hairy parts of science like biology, where it's so expensive and hard to like get this data. I think that is a limitation. I think there's ways we can start building around that and going beyond that. But yeah, that's definitely one space, especially in biology, where a lot of data and really consistent data is actually so hard to get. Like you can also try and bring the world's data together on a certain property for a molecule, for example. But these properties have been recorded by different labs in completely different ways under different circumstances. And, in the limit, your model will have to understand all of these things to really accurately model that data. So that's really hard.
Yeah, I think from my perspective, I think, it's kind of, I think the large language models thing is quite amazing, to be honest. I think when I first, I had colleagues at UCL who were a few years ago trying to use autoaggressive style models to predict the next token for, say, a computer program. I thought it was totally nuts. Like, oh God, there's no way that's going to work. How can you possibly, get the parentheses matching correct and all that kind of stuff and the syntax? And actually, it's quite amazing that it works as well as it does, even though it's not perfect, and there are definitely limitations around that. And I think it's kind of easy to forget that it's about 2 years since ChatGPT came out, and people are already, it was amazing sort of milestone, right? It's incredible technology, but people get quite sort of they already have moved on to the point that it's not good enough. There's kind of like clearly there are challenges around those kinds of models, and I don't know if we're going to be able to solve that actually fundamentally along the way that we're going right now. Somehow I feel that the models themselves, the way we train those particular language models, may be not easy to fix. If you want to say, well, I want some kind of perfect reasoning system, I don't want it to hallucinate. It may be very challenging because we may need a different kind of paradigm if we want to do that. But I do think this maybe goes a little bit back to the agent kind of situation as well, that these models, maybe they're a little bit like ours, maybe they're generally good at knowing a lot about many different things, and they have some kind of, good reasoning capability, but they're not perfect. But can they recognize, when they need some specialized input? So they might say, well, okay, I need to call a particular tool like a calculator or a database lookup or some real factual thing. And as long as they're able to do that, reasonably consistently well, and then you get the benefit of both this sort of high level, amazing vast knowledge across so many different topics and fields, but you combine that with the sort of the specialized, accurate knowledge that you may require in certain domains, then there's obviously a massive potential there. So I think it's a very exciting juncture that we're at. I think a lot of people are sort of feeling that there's been a huge progress. We can throw more computes at the problem, but the architectures are, I think, broadly the same, because we don't know exactly what the big tech labs are doing. But it seems like a good insight is that probably they're all very, very similar transformer-based underlying architectures. But are we waiting for the next big thing? Or is it going to be just an evolution from the current framework? Who knows? But that's obviously, if we can marry those things together to get rid of some of the hallucinatory challenges around large language models, then I think that would be an amazing situation.
Yeah, and it's really interesting actually, David. You're talking about this for large language models. Of course, like hallucinations, you see this in all models. It's in like normal language, we often just call this errors, right? And the like models, even like AlphaFold, they hallucinate, they make errors, like these statistical machines at the end of the day. And like can you really trust them all the time? And this is a big limitation. Like the really cool thing, especially with like some of these scientific domains, is that actually verifying that a prediction like is accurate, is true or false, can often be much cheaper to do in the real world than to create the prediction itself. And this is a property that's like common across like quite a lot of different spaces in science in particular. David, I think as well, you touched upon this as like calling these expert systems, like calling the databases, like popping down into the real world where you need to, like to verify. This can be a very, very like powerful mechanism and much cheaper than doing the generation of the actual result itself in the real world, which gives me hope.
Yeah. I think also, people are, if you're using these systems in the real world, I think people are very sensitive to confidence or uncertainty in these things. So, if I had a colleague at work and I asked them about something and they're very confident and say, oh, this is the believe me, this is how it is, this is the answer, and they get it right, fantastic, wonderful. That's really good. But if they get it wrong and they're super confident, then that, I think people are hypersensitive to this. We kind of get very easily wary about overconfident colleagues that can be wrong. So I feel like I know people are looking into this and it's challenging, but research into how models can express more meaningful senses of their confidence or uncertainty in their predictions will be very, very useful for our sense that we can trust. It's fine if the model says, look, I'm not sure about this. That's a much better situation than saying, look, believe me, this is the case. And being overconfident about that.
Thanks both. I think pushing you both a little further on this, I think it'd be great to understand what models aren't perfect and the technology isn't perfect and it likely never will be. How do we think about creating minimal viable products and creating products out of this not perfect technology? And Natalia asks a question that moves along this route to think about how do we take something that is a highly theoretical research paper into something like AlphaFold to an actual product that you can sell. So we'd love to dig into thinking about these big imperfect technology pieces and how do we move that into something that's actually useful for your average person?
Yes, this is super interesting. Probably the worst space you can be in is something like a self-driving car, where you need to get to like 99.999% accuracy. Otherwise, you can't deploy this. But thankfully, like there's many domains where you like the baseline computational technique might be actually not very good, and quite poor, and maybe like no better than random or only marginally better than random. If you're lucky enough to be in that space, and even if you've got like a 70% accurate model or 80% accurate model, there should be signal there that no one else has, or that you can like create real value from. But the question is, how do you like get at that signal, and how do you actually like utilize that to create value? And I think this speaks to my point of like deeply integrating and vertically integrating these models into a product or into like a workflow or system that creates value. Is if you just use the end prediction of 70% accurate or 8% accurate, your customers are going to get pretty pissed off, right? But there is differentiated signal there, and so working out how to extract that, how to like massage that into a form factor that actually does give people something that they want, I think is like is that one of the big challenges here, but the thing to focus on. So yeah.
Yeah, I think for me it's difficult, right? I mean, I think in the beginning, maybe, you know, of this LLM sort of revolution, and I think people were very relatively forgiving about these systems. So it's just amazing, right, what they can do, really. It's kind of like, I think the novelty was huge, but it's kind of, I think, worn off a little bit. So if you want to say, create a poem or, you know, some kind of very highly creative thing, then it's fine. But if you're an enterprise and, you know, you have much more strict concerns about, you know, how these systems are used in your organization, and they need to be compliant, and they can't do things, you know, it can't go off piste here and there. So actually, getting them to work well is really been quite you know, an interesting challenge. And I think it goes back a little bit to this uncertainty situation. So if we can somehow get a sense of, you know, how confident these systems are in their outputs, then fine. If they're not very confident, then a human sort of, you know, jumps in and takes over at that point. And hopefully eventually there's a feedback system where the machine starts to understand, you know, okay, I wasn't very confident here, but, you know, this human told me that's the right thing to do, and they continue. But I think another thing which is very, I think, underutilized at the moment is that the kind of feedback that people have used to train these systems and currently in machine learning, you know, we kind of very used to the idea of like right and wrong, right? So somebody says, oh, that's a cat or that's a dog. You know, we have these labeled data sets, or in RL, this is like, you know, this is a good or that's bad, and it's fine, but in some ways it's kind of impoverished feedback, really. You know, you I think would like to think that I could explain to you why you're wrong or why this thing didn't work properly. You can say, well, yeah, it's actually not a cat, it's a tiger. Because I know, you know, they look similar, but there is a difference, and I explain what that difference is. And if it's a smart machine, surely my richer, you know, feedback should be able to accelerate understanding of the machine to actually to do better. So I feel like that human computer interaction through richer feedback has not really been a sort of a particularly well explored area yet. And I think there is definitely scope there. And it's about dealing with uncertainty, but then taking, I think, richer feedback to help more rapidly understand what the problem is.
And, you know, maybe to build on this, and also like with respect to this question that just came in on, you know, like how do you commercialize this, an imperfect model? Like how do you think of an MVP? Like, you know, especially as like the field is like continually moving, and, you know, you want to be developing your model to be better and better and better, but at the same time you actually want to create a product out of this thing. You know, like I often think, can you just like start to predefine the API of this model? Like what are going to be like the concrete inputs and outputs of this? And if you can set that, then you can allow, you know, model development to increase the accuracy of this to happen in parallel, or maybe if you're waiting for a new language model to come out, you know, that can happen in parallel while you're going off and creating like the product and the, you know, the experience that occurs around this API. And that's the deep vertical integration I was talking about. And, you know, maybe in the world of like when your model is 70% or 80%, you actually have to rely on human input for some stages of that product or process. But then over time, as in parallel your model is getting better, you can lift more and more of those, like, you know, human touch points, and but the API remains exactly the same. So that could be a nice way.
Max, just a quick question that's come in through the DMs. Can you explain vertical integration and how you think about it in context of isomorphic?
Yeah, so I mean, we can, you know, you can think of, okay, we've got this model AlphaFold 2. Actually, this doesn't, you know, serve full purpose for drug design, so we need to create AlphaFold 3. And, you know, there is a whole research project and a huge amount of effort on creating AlphaFold 3 and making the accuracy better and better and better. But at the end of the day, this is a model where you put as input, you know, sequence of amino acids and molecule descriptions, you get a 3D structure as output. That doesn't design you a molecule, right? And that doesn't help you create a industrial grade like molecular asset that you can, go out and sell. So, if we wanted to vertically integrate AlphaFold 3, we've got to think, okay, well, like how can this model actually have impact on the drug design process? We need to go in and look at like how chemists are doing things now. Is there an opportunity to like pull this model into part of that normal workflow? So chemists will like have hypothesis, feed that into the model, take those outputs, then keep going with their normal drug discovery process. So, really embedding this model into like an existing pipeline of activities would be an example of like a vertical integration of AlphaFold 3. Those activities include, working out what target you're going to work on and interacting with wet labs and verifying results. So there's huge amounts of complexity that's beyond just the model itself, but the model is maybe a key part that gives you your full pipeline like a differentiated, capability or differentiated efficiency or speed or something like that, if that makes sense.
Yes, very much so. Perfect. Thank you. Okay, looking through some more of the questions here. Germain's a fan of your work, David, your book on Bayesian
great.
reasoning.
Thank you.
That being said, he asks, in the current era of LLM hype, what is the place of Bayesian ML or other methods, both on research, but let's focus even more on startups in terms of this conversation?
Yeah, I mean, it's difficult, right? I mean, but the Bayesian thing, in some sense, it's a nice framework. I mean, just partly, by the way, I should say that my initial title for the book was, I think, probabilistic modeling and machine learning, something like that. And then I got a message from Kevin Murphy, this is back in around 2000 or whatever, saying, well, he's also writing a book with exactly the same title. So, we were going to join forces or do it our own ways. And we decided that, well, I sort of decided maybe I didn't want to join with him. But then I had to come up with I let him have the title. So I needed a new title. So I came up with this, Bayesian sort of reasoning title, which I think to some extent, I would say it was more, I think about, not just the sort of the typical Bayesian thing in terms of parameter learning, but it's more the general probabilistic modeling framework. So obviously it's challenging to do, say, full-scale Bayesian reasoning, right, with a deep learning environment, unless you're looking at, say, some very restricted form, like just the parameters of the final layer or something like that. But I do think, there are, and going back again to the uncertainty thing, I think it is part of the potential answer, right? I'm not necessarily saying, it's easy to do this, but if we can in some way get a much better senses of uncertainty, whether or not that's through the Bayesian approach or something related to that, I think that's obviously, a valuable thing. And I think also that, it could be useful for generally when you're thinking about, which models work well, which models don't work well, right? In some sense, there's still this kind of intrinsic sort of Occam's razor style effect of the Bayesian approach, which if you can apply it, I think is very useful. So I'm not sure. I mean, I think we've seen very nice applications of Bayesian modeling. I quite like Stuart Russell's work a few years ago, where he was trying to look at earthquake modeling, I think for the United Nations, and he used kind of a Bayesian approach there, and has a wonderful sort of models of the sort of the propagation of these ways through the Earth's crust, and trying to figure out then where the sources of the sort of the explosions might be in, and also whether or not they're nuclear, the sort of signature of a nuclear explosion. So I think there are, I don't think it's going to go away. I think there's a huge role for Bayesian techniques, but marrying them with deep learning is, and probably will always be quite tricky.
Yeah, absolutely. I agree. And adding to that, I think there is a question around, so some of you have this research background, and a lot of the people here are experiencing having research backgrounds and wanting to continue that research and being quite excited about that research, but also looking at transitioning to the startup space. And so there's a question for David, but Max, I think you've also gone through both academic and startup experiences and think about balancing your work in terms of your goals. So as academics, you must have worked quite a lot to transition from academia to industry, especially startups. This is to David. But how do you find the right balance between running a company and running a research lab? Do you have any recommendations on this front? And so generally, if either of you have thoughts on the realities of research when it comes into the context of being in a startup.
Yeah, so I mean, maybe I should say to start with that I've not really run a company. You know, the typical thing is I've been very fortunate to have, you know, great students, and I sort of maybe come up with an idea with them, and we work together on it, and they typically, you know, take over at some point. So I would say I have huge experience in running it, but I've seen what's happened and then trying to run with it. I think a lot of academics like myself in the beginning, you know, we were a little bit naive. We think, oh, wouldn't it be great to, you know, have this startup company and we can sit around with our feet up on the desk thinking about how we're going to solve the world's great problems and it's going to be fun, right? But actually, you know, you quickly hit the reality that you need to start building stuff, right? You know, and it's in an imperfect world and with imperfect knowledge about whether or not this thing is going to be the right direction to go. But what I can say is that commitment is really, really important, both in the academic sense, but also in the startup sense, right? You have to really commit to this idea, and it may not necessarily work out in the sense that you may need to change a little bit. You know, you may need to pivot to something a little bit different. That happens as well in academia. You know, sometimes we start off with the best intentions and it doesn't work out. But I think there are some very good characteristics that academics have, which are very, very useful in business, which is a kind of robustness. I think, you know, if you're somebody who's easily disappointed, you will really struggle to get along with an academic career. You know, many things we do don't work out. You know, it's a very critical atmosphere. There's very few people sort of, you know, slapping you in the back saying, well done, that's great. And so we kind of, there's a stoicism, which I think is sort of built into your average academic, which I think is also very useful in the startup world because you'll get a lot of knocks. You know, many of the things you try won't work out. But if you have that passion as an academic, you might say, well, okay, that particular project is not working well, but I still know why I'm here. I love machine learning. I love AI. I think it's a really worthwhile end goal. If you have that similar kind of, you know, passion for your startup idea and really where you want to get with it, even though the path may change, I think that's a very, very important thing to have.
That's really interesting, David. I may be like slightly the wrong person to ask here. Like when I sort of accepted my PhD and to do that, I sort of said to my supervisor, Andrea Zisserman, I said, I'll do this, but by the way, I'm going to be spinning out a startup from this. So it's like from day one, you know, wanted to build sort of companies off the back of this technology. But I think like both environments, and especially academia, like as David said, like amazing like breeding grounds and proving grounds for, you know, especially companies built on completely new technology, like very good environments to have that space to explore, to like really push something down a path that, you know, no one's been down before, and do that in a protected way. And of course, like you can do that in industry as well, but there'll always be that, you know, back of mind in industry of how does that translate into, you know, product or you know, something that's going to like impact the success of this business. So I think there's like a huge amount of space for people to be operating in both of these environments. And, you know, I think, you know, you should really think as an individual, like what is that bigger mission that I'm trying to go after? Like what is the sort of change I want to affect in the world? And, you know, for each point in time and for even each, you know, specific niche or field, that might mean, hey, actually academia is the better place to do that right now, or maybe industry is the better place to do that. And I think we've seen with you know, especially like, you know, the field of deep learning, that can sometimes switch. and sometimes switch back as well. So yeah, it's really interesting to see how this evolves.
Well, one I think for me, which is very inspiring about all this is, I had the feeling when I was quite young, and there was a much sort of greater separation between academia and industry, and I think sometimes there was a sense that if you want to be good at business, you got to be made of the right stuff, and you need to sort of like be confident and have a sharp suit, and this kind of talk the right kind of business language and all that kind of stuff. But now, actually, if you just look at the world, right, the biggest tech companies are led by people who have tech backgrounds, right? Zuckerberg, the Google guys, they're all highly technical people. And there's never been a better time, to actually enter business with deep technical skills. And I think it's great. I love that. I love the captains of industry are dominated by people with deep technical skills, and I think it's really a testament to the ability of scientists to actually also do business.
Yeah, totally. And it's like that ability to be able to pivot and build into something. Like if something doesn't work down one angle, be able to actually move and build down another angle. If you have the actual technical skills, you're really well positioned to do that compared to someone who actually doesn't.
Incredible. Well, I think this is a great place to wrap it. That has been a well-rounded part of our conversation. I think it's something that we can all ask ourselves. What is the change that I want to affect in the world? I really liked that, Max. And I think it's something that a lot of the participants here have been asking throughout these sessions. So thank you, David. And thank you, Max, for this incredible conversation. I think we're all walking away with a lot to think about. We've learned a lot about building companies off the back of this incredible technology and the challenges that come with pushing something down a really unknown path. And that's what this session and the last 3 sessions have really been about. So thank you so much.
You're welcome. It was a great pleasure.
And so with that, I'm going to share the screen one more time and just remind everybody, this was Max Jaderberg and David Barber. So thank you again. We're so happy to have had you. Cohort applications are open for our cloud cluster. So please send in your applications. The deadline has been extended to October 31st. I know there's some issues with the link. It is live again. Please submit if you have any difficulties. You know where to find me in the Slack chat. Beyond that, we still have one more session tomorrow. It's a practical lab, so come with your questions. We're going to hear from Parasul Patel, who does a lot of our go-to-market strategy with our portfolio companies at Radical, as well as Sean Gardner, who is with Weights and Biases. So he has a lot of product background and information for you. And so come with your practical questions. And that's it for today, folks. You know where to find me in the Slack channel, and have a safe evening or morning, depending where you are, and take care. Bye, everyone.